Yeah, she finished this PhD at University of Illinois at Urbana-Champaign with CTET, and he worked on a number of, I think, influential papers, including, I think, one of the best paper in detecting out of distribution samples, and also influential paper in understanding representative power of neural networks, landscape analysis, and he just studied at UW as a postdoc, I guess officially today. And yeah, I hand it over to you.
Hi, everyone. And actually, this is my defense slides, so it would be kind of like formal. But if you guys want to say something interesting or if you want to ask any questions, so please feel free to ask. And the title of this talk would be the role of the explicit regularization in over-parameterized neural networks. And this work is advised, actually it was done during my PhD, and when I was supervised by Professor Shrikant at University of Illinois at Urbana-Champaign. Okay, and this is the outline of the whole talk. And first, I will give a brief introduction of what we are doing, and then we're going to give a brief overview of the prior work, and then we're going to introduce our main results. And based on that, we are going to give a kind of like the sketch of the proof idea. And after that, we are going to conclude the whole talk and present some future work. Here's the introduction. I will give a very quick introduction of what is the neural network. And here's the single neuron. The single neuron takes a single input, and it gives out a scalar output, which is the sigma x, where the sigma here denotes the activation function of the neuron. And here we illustrate two types of neuron, which is used in practice. The first one, the left-hand side one, would be the rectified linear unit, which is what we call the ReLU. The ReLU takes the scalar input and it outputs 0 when the input is basically negative, and it outputs the input if the input is basically positive. And the ReLU is basically the square version of the ReLU, which is also a smooth version of the ReLU. And if we have multiple neurons and if we are connecting them together, we will have a multiple layer neural network. And here, this is a multiple layer neural network of the L layers. The X would be the input, and the Fx theta would be the output of the neural network. Here, the theta denotes all of the parameters in the neural network. And during this talk, we are going to mainly focus on the binary classification. Assume we have n data samples, x1, y1 to xn, yn. Here, each of the x can be viewed as the image or the text, or doesn't matter. It's kind of like the d-dimensional vector. And where the y denotes the kind of the label. For example, if we are trying to classify the images of dog and the image of cats, and here the x denotes the input matrix of each of the image, where the y denotes the label, where the -1 can denote a cat and +1 denotes the dog. And during the training, we're trying to find a neural network parameter theta, which can minimize the misclassification rate, where the misclassification rate is defined here, which is basically the average rates where the neural network misclassify the training samples. And as you can see, because this misclassification rate function is highly non-differentiable, and it is very difficult to minimize. So typically what we are trying to do in practice is we are trying to minimize the surrogate loss function. And usually we will choose the surrogate loss function L, such that the Ln theta is basically an upper bound of the Rn theta. So this means if we can find the theta such that the Ln theta is very small, then at that case, the Rn, the misclassification rate, is also very small. Okay, so here we want to mention that the traditional wisdom of the statistical learning theory and what is happening in the real practice for the neural network is somehow there's a small gap. So let's consider the problem. Let's just find let's okay, assume we have n data samples, x1, y1 to xn, yn, and now we want to find the function f theta x such that the f theta x can approximate the label y for each of the data samples. Here, the theta denotes the vector of the parameters. The f theta can be anything. It can be linear. It can be anything. Here is just, we illustrate some examples for this, which is basically linear, but it doesn't matter. So the traditional wisdom tells us the dimension of the parameter vector theta should be smaller than the numbers of samples because we don't want to overfit the data, and we want to control the model complexity, and at the same time we want to minimize the training error. So at that time we believe that if we can do that, then the result can generalize well. So this is what the statistical learning theory tells us. However, what is happening in the real practice is, what we usually do for the neural network is the neural network is usually very large. And the dimension of the parameter vector for each of the neural network is far larger than the numbers of the data and the data sample, the number of the data samples. So, and in practice, what we observe is the neural network can easily fit almost of the data samples. So this means the training error is very close to 0. And however, it can also generalize very well. So the question is why? So in this talk, we are trying to give some answer for this question. So here we provide some examples of the over-parameterized neural network. And these are the 4 types of the neural networks trained on the ImageNet. And the ImageNet have the 40 million images. However, and here we are providing the numbers of the parameters for each of the neural networks. So basically, you can see that the numbers of the parameters is basically larger than the numbers of the samples in the data set. And you can also see that the top accuracy is reasonably good. So basically, this means in the practice, the numbers of the samples is smaller than the numbers of the parameters in the neural network. So we're in this talk, we're going to give some explanation for what is happening here. So there are several challenges for answering this question. So because the loss function is a highly non-convex function and of the parameter vector theta, and the dimension of the theta is also very large. So it is very difficult to analyze it. And actually, there are 2 perspectives of the challenges. The first perspective is what we call the memorization. So in the memorization perspective, we want to find an optimization algorithm. It's basically like a problem of the optimization. We want to find the optimization algorithm to find the goods local minimum of the non-convex minimization problem. So here, the definition of the goods can be in different kind of style. So you can define the goods as the training error would be very small, or you can also define the good to be the training loss would be very small, or you can define the goods local minimum as a local minimum where it has some kind of special properties. And however, in this talk, we are just going to consider the local minimum with small training error or with small testing error would be the goods local minimum. And so this is basically the first part of the challenge. We want to, this challenge is more like an optimization problem. And the second one would be more like a generalization problem. So the question is, okay, assume we have a good optimization algorithm and it can give us a set of parameter which can have a very small training error. However, we're asking, okay, if we are showing this neural network with some classification task, which is not part of the training set, and does this neural network still have a very good performance? So does this neural network still generalize well when the training error is very small? So basically, there are 2 parts of the challenges. Okay, now we are going to get into the details of these 2 challenges. So for the memorization, what we observed in practice is the loss function is highly non-convex, but the gradient descent algorithm usually find over-parameterized neural network memorizing almost all training samples. And so basically there are two types of the recent papers going on. The first one, the first type of papers focused on the local landscape, and they want to design the algorithm which can escape the set of points, and they want, or they're trying to prove the local convergence of the gradient descent. And later we will get into the details of this type of the papers. And the other kind of papers focused on the global landscape of the loss function. So our approach is basically like the second one. So we are focusing on the global landscape, and we are trying to characterize the properties of all of the local minimum. Okay. And for the generalization, we in practice, we observe that the over-parameterized neural network usually generalize extremely well in practice. However, the traditional learning theory tells us that simpler models have better generalization performance, like what I've said. The other papers showing kind of like showing that the appropriate initialization is basically the key, and later on we will get into the details of it. And our approach is basically different, and we are trying to understand the gradient descent, when the gradient descent will lead to a good local minimum. And here what we mean the goods is the generalization performance is very good, or the small or the testing error is very small. So the way we are trying to analyze it is we are trying to exploiting the properties of the global landscape. So for the memorization, we are trying to show that for each of the local minimum, it has some good training performance. And in the second part, we are also going to show that at every local minimum, the generalization performance is also very good. Okay, now we are going to have a brief overview of the prior work. Okay, and the prior work shows that the over-parameterization can allow us to easily feed the data and get very small training error and testing error. And the way they're showing that is that they're pointing out that the clever random initialization would be the key. And if we're using a very good random initialization, and we will have a global convergence of the gradient descent or the stochastic gradient descent. And here are some kind of work we're providing here. And also, and before this talk, and Adam says, there's kind of like something, I don't know what is something going on with the implicit regularization, but they are trying to show that when they're actually, the way they're showing that the gradient descent will lead to a very good generalization performance, and they're basically using some notions from the implicit regularization. Although there are some kind of like debates on it, but we don't know. And however, theoretically, the numbers of the neurons they require is unreasonably large. And later we will get into details of it. And there's a work from G and Targowski at University of Illinois at CS department. And they show that they can use a small number of neurons if the two classes are well separated. And if the two classes are not well separated, or if they're kind of noisy labels, then the numbers of neurons they require is basically is also very large.
Shiyu, let me just ask for just some clarification. First, the local and the global minima that you're talking about are for the training loss, right?
Yes, correct.
So it's not even clear, like if you can find the global minimum of the training loss, that it will generalize.
Yeah.
And also these papers, when you say get small training loss and testing error, these papers that you've cited take additional assumptions in order to get small test error.
Yes.
Like they basically assume that whatever GD finds has small complexity, and so then you can get the small.
Yes.
Yeah. Okay.
Okay. And the key idea in the prior work, like the Adam said, is basically they're using some notion from implicit regularization. And basically the way they're doing it is they initialize the the parameters very well, such that many weights of the neurons are closest to the 0. So this means the norm of the this W is basically can be bounded. So what they're trying to do here is they want to control the model complexity. And next, they're trying to linearize around the W0 and use the gradient descent to ensure that the W infinity, which means when we are running the gradient descent, then the W infinity means the gradient, the output of the gradient descent at the infinite time. And so this means so what they're trying to show is during the training, the gradient descent won't make the parameter diverge far away from the initial point. So this means that WT minus the W0 is kind of very small during the training. And they can also show that during the training error is also very small. So we have two parts. The training error is very small and the model complexity is basically bounded. And by combining the two of the properties, we can show that they have the good generalization performance. And of course, they can only show that under some specific assumptions, like for some type of neural network or under some kind of data assumptions. And for this prior work using the implicit regularization, the numbers of the neurons they require is unreasonably large. And for the regression problems, they use at least n cube or higher. And some prior work like G and Targowski requires like full separation between the different classes. And most of the prior work relies on some special choice of the initialization strategy. And basically you have to use the Gaussian initialization of very small variables. And our goal here is totally different. So we are asking the following three questions. So the first one is, can we use the implicit regularization to use far less neurons because they are using the n cube or higher? And however, like I have illustrated, for the image nets containing like 14 million numbers of samples, and however the numbers of parameters in each of the neural network is basically have the same order of the numbers of the samples in the image nets. However, here they're saying that they need n cube, and so basically this is not happening in the practice. So here we're saying that can we use the explicit regularization to use the far less neurons like n+1 neurons. And at the same time, we're also asking the following question: can we use the explicit regularization to help learning the data set, which may not be fully separated? Because in the GT and Targowski, they require the far less neurons. However, they require the full separation. So this means if the same sample if the two samples with the same feature vector, however, their labels are totally different, then in this case, the G and Targowski requires the infinite numbers of neurons. So we are asking, okay, is it possible to use the explicit regularization to help us learning while they're kind of like noisy labels? And the third question is it possible to find an algorithm to find good points in the polynomial time, which can start from any bounded initial point? So basically, the prior work heavily relies on some initialization strategy, and they're requiring that the norm of the initial point should be kind of like bounded, should kind of be very small. So we are asking here, what happens if we can start, is it possible to find something which enable us to start from any bounded initial point? So basically we do not depend heavily on the initial points. And these are the three questions we are trying to answer today. And our prior work at the NeurIPS 2018, we proved that adding one more special neuron can easily eliminate all of the bad local minimum. However, later someone else shows that the descent algorithm may diverge to the suboptimal point at the infinity. So there's a huge issue at the infinity. And later on, we published another paper, and this paper shows that if we're adding a cubic regularizer to the loss function, and basically it can eliminate all of the bad local minimum. And at the same time, because this cubic regularization regularizer has all of the parameters in the neural network. So this means it's a kind of like coercive function. So this means the descent algorithm won't diverge in this case. So basically, we're trying to fix the infinite issue. And but this work requires using a type of the smooth neuron, which is not widely used in practice. So basically, we're using the ReLU, which is the squared version of the ReLU, which is not used in practice, which is not good. And we also do not have a result in the generalization performance and the algorithm. And so this is something we are trying to provide today. And today we're trying to use the L2 regularization. The L2 regularization can be viewed as a weight decay in some form of the weight decay, so which is widely used in practice. And also, instead of using the n cube or higher numbers of ReLU, we are just using the n+1 ReLU neurons, where the n denotes the numbers of samples in the training set. And ReLU is basically widely used in practice. And we are also providing the performance analysis on both memorization and generalization. And we're trying to show that the training error is very small, and the generalization, the testing error is also very small. And we are proposing a variant of the gradient descent, which can find the good point in the polynomial time. And it can start from any bounded initial point. So here, what we mean here is, the good point here is more like a point with the guaranteed generalization performance. Actually, in fact, when I'm trying to analyze the gradient descent or some variant of the gradient descent, it is very hard to show that they can find a local minimum, because some other papers like Adam's paper have shown that sometimes under some conditions, finding the local minimum would be an NP-hard problem for some cases. So we're not trying to do that. And our main results, here we provide an overview of our main results, and later we will show what exactly means. So basically, in this talk, our main result shows that with an appropriate L2 regularization, the number of the neurons in the practice, we only need n+1 numbers of ReLUs, and we can show that the average local minimum of the loss function leads to a very small training error and very good generalization performance. And we can also show that there exists a variant of the gradient descent requiring only bounded initialization. And it can guarantee, and we can also show that it will find the good points in the polynomial time. Here, what we mean good is it has a guaranteed generalization performance. Okay, now we are going to show our main results. So before showing the results, we are going to go through some basic notations we're going to use. In this talk, we are only considering the single hidden layer neural network, where the F is basically the output of the neural network, and the AJ is basically the coefficient for each of the neurons, and WJ is the parameter vector for each of the neurons. And during the training, we are going to train both of the AJs and the WJs. And the neuron we are using in this talk is ReLU. And the theta denotes all of the parameters in this neural network. And the assumption for the loss function is as follows. We are assuming that the loss function, the L, the univariate loss function, is convex, non-decreasing, and twice differentiable. So basically, we provide two type of loss function here. The first one is the logistical loss, and second one is basically the polynomial hinge loss. And for the data sets, we have two cases. The first one is the realizable case. So basically, we're saying that we assume that there exists some neural network in our class such that it can classify all of the samples with some margin gamma, which is the realizable case. So this means the data distribution or data sets can be full separated by some neural network in our class. And we are also considering some unrealizable cases. So we are saying that with high probability, at most epsilon, the neural this data distribution cannot be separated by some neural network in our class. So this means with high probability, the data distribution or the data sets can be separated by some neural network in our class with some good margin. And this is the data assumption on the data set. And the loss function we are considering here is the first part is basically the surrogate loss function. And second part is the L2 regularization. And instead of using the homogeneous coefficient, homogeneous regularization, we are using the different coefficient for each of the neuron. And actually, there are other recent works presenting some property of the explicit regularization, and here we provide two. But actually, they're trying to focus on the difference property of the explicit regularization. Now, some papers focusing on the what is the performance of the global minimum of the loss function when we are adding some explicit regularization, and some others focusing the other kind of perspective. But here we are trying to focus on our we are trying to analyze the regularized loss function in a different way.
Shiyu, can I ask a question real quick?
Yeah, sure.
Mine was just a clarification question. What was the A here again?
The A is basically the coefficient for each of the neuron.
Ah, gotcha.
Yeah.
Sorry, just for me also to understand. So you say that I add one more neuron and then all local minima generalize well?
Oh, no, we're not saying that.
Sorry.
That's a different paper.
That's a different paper.
Okay. So I'm confusing the papers. So in your result here, you can find the local minima easily or not?
Later we will show that the finding okay. Generally speaking, finding a local minimum would be an NP-hard problem. So we cannot do that. And later,
even checking if a point is a local minimum is NP-hard in general, but I don't know what you're assuming here.
Okay, and so later you will see that instead of, okay, first we will show that every local minimum is good, and then we're asking the following question: what kind of property does the local minimum have such that it has a good training and generalization performance? And later we will show that there are three kind of properties which enable the local minimum have it. And then instead of finding a local minimum, we just need to find the point which satisfy those three properties. And then we provide some algorithm which enable us to find the point which satisfy those three properties, and that's it.
So end to end, what you said, if I understand correctly, says there is a polynomial time algorithm that will find a point that has three properties, and if a point has three properties, then it generalizes well.
Yes, correct.
Therefore, I can, in polynomial time, find a point that probably generalizes well if I have n+1 neurons.
Why?
No, I'm asking you. Is that what the result is, that I can find?
Yes.
Okay.
Yes,
okay.
correct.
No, I mean, you need additional assumptions. I mean,
yes, of course I need additional assumptions and additional structures on the neural network to make it true.
Okay, great, thank you.
Yeah. Later.
So sorry, I have a question.
Yeah.
Could you go back to your last slide? So yeah, so no, the theorem.
The theorem, this one?
Yes. So you said you have this regularized loss function, right? It's the sum of the training loss, the actual data loss plus the regularization.
Yes, correct.
And then you're saying that the overall loss function has some bound, right? But then you really care is the data loss, right? Because if the regularization term dominates, then obviously you could get something very good, right?
Yes, correct. So this is what the theorem says, because later you will see that you see the okay. Let me present this theorem first, and later we will focus on your question. So what this
actually, sorry, just maybe just an even easier question, like for your theorem here, let's say that you had a global minimum. Is it obvious why that even that generalizes?
Yeah, of course.
Why? It's just the global minimum of the training set.
The global minimum of the training sets may not generalize.
Right. So I'm saying here you have a theorem about the generalization properties of the local minimum. I'm saying, is it clear? So obviously the global minimum also satisfies these generalization properties.
Yes.
But is it easier to prove the global minimum has this type of training error, has this type of generalization error?
Actually, no.
Oh, interesting. Okay.
Actually, no. So, yeah. So later you will see that basically the properties we are using actually do not require any kind of knowledge on the global point, on the global minimum. So basically, every property we are using is directly from the definition of the local minimum.
Cool. Thanks.
Okay. So let's focus on this theorem. So this theorem says that if the m is larger than n plus 1, and if the n is large enough, and later I will present the theorem showing that if the n is not large enough, and what is happening. And then for almost all lambda j's in this interval, the following results hold. The first one is the empirical loss function is coercive. So we are trying to present this because we want to show that because the function is coercive. So this means no matter which way you're trying to, no matter which direction, in which direction the parameter diverges, then the loss function always increases. So this means the gradient descent always converges for this loss function. And second result shows that every local minimum of this loss function has a training error of this. And this training error has two parts. The first one comes from the data distribution. The gamma here denotes the margin, and the epsilon denotes, let's get to the, okay. So here we are assuming that the data samples can be separated by some neural network in our class with some probability, at least 1 minus epsilon, and with some good margin gamma. So here, the first part of the training error comes from the data distribution itself. And the second part comes from the regularizer. So basically here you can see that if the lambda j is very large, if the lambda j, the maximum of the lambda j is n, then the training error would be 1 over gamma, right? It would be a constant. It won't be very small. So this means the choice of the lambda j here would be very important. If the lambda j is very small, if it is close to the 0, so then later on you will see that we are not able to control the model complexity. Okay, and however, if the lambda j is very large, of course we can control the model complexity of each of the local minimum. However, the training error would be very large, right? So this means there's kind of like trade-off of how you choose the coefficient of the regularization. And does this answer your question regarding to this lambda j?
So assuming the loss function should be normalized, right? Divide by n and divide by m, I guess.
Divide by n, yeah.
Oh.
So
And this, so you're saying when n is large, the second term is going to go to 0?
No. So this totally depends on how you choose the lambda j. If the lambda j has the order of n, then the second part is definitely constant, right?
Right. So what's the choice of lambda you're going to use? I guess.
Later I will show that. Okay, if the lambda j is very small, then the model complexity cannot be bounded. So this means the generalization error won't be very small. And if the lambda j is very large, the model complexity can be bounded. However, the training error will be very large. So later I will show that the optimal choice would be the square root of n. So this means the second part would be 1 over gamma times square root of n. So this means if the n goes to infinity, the second term goes away, and we only have the first term, which is only related to the data distribution itself. Okay.
I see.
And then because this theorem has an issue if the epsilon is kind of 0. So this means if the data distribution is fully separated, then it seems the numbers of samples we require is kind of infinity, and the numbers of neurons we are using basically infinity. So it is kind of it is really confusing. So basically here we are providing the second part. So if the epsilon is very, very small, and if the n is not large enough, then the upper bound becomes like this. Instead of having the epsilon here, we are having the 1 over square root of n here, because the 1 over square root of n is basically an upper bound of the epsilon. And still, if we're choosing the maximum of the lambda j equal to the square root of n, then the whole part will goes away as the n goes to infinity. Okay, so this is the first part of for the memorization. And this is the second part for the generalization. And still we are using the same empirical loss function, and the numbers of neurons we're using is n plus 1. And we are assuming that n is sufficiently large, and later I will have another result showing that if the n is not sufficiently large, then what is going to happen. And for almost all of the lambda j in this interval, so this kind of answers your question. So basically there's an upper bound for the choice of the lambda j, and there's also a lower bound for the choice of the lambda j. So it cannot be too large, it cannot be too small. So there's a trade-off of it. And for every local minimum theta star of this empirical loss function, the testing error would have this kind of order with probability at least 1 minus delta. And so the first part comes from the basically comes from the underlying distribution, and the second part is basically combined of two things. The second part comes from first the upper bound for the Radon complexity, and second is from the remaining part for the McDermott's inequality. Okay, and if the n is not sufficiently large, or the epsilon is very close to the 0, or it is 0, then for almost all lambda j's in this interval, so you can see that the choice is slightly different. And for every local minimum theta star of the empirical loss function, the testing error has an upper bound of this, and it holds with probability at least 1 minus delta. So this means if the n goes to infinity, then this upper bound goes to 0.
Sorry, what's the gamma again?
The gamma is the margin. This.
Oh, okay.
So with probability at least 1 minus epsilon, there exists a neural network in our class, and it can classify the underlying distribution with some margin gamma.
Okay, and the empirical loss of for the local min doesn't appear in your generalization bound anywhere.
Yeah.
Isn't that why is that?
Because so what are you saying that this won't appear in our generalization bound, right?
Yeah.
Okay. Actually, it appears. Okay, let's consider for this.
Oh, I see.
So this is the
because of this theorem. I see.
Yes.
Okay, I see.
And we are also choosing the lambda j have this order of the square root of n.
All right, I see. Thanks.
So the first part appears here, and the second part appears here. And okay, we also have this. Okay, for the algorithm. Assume the m is larger than n plus 1, and assume that the n is sufficiently large. And then for almost all of the lambda j in this interval with probability at least 1 minus delta, we can show that for many interesting classes of the neural networks, there exists a polynomial in both n and dimension d. N is basically numbers of samples in the data set, and the d is the dimension of the feature vector. A time algorithm to find a point theta star such that this holds. So actually, we cannot show that under this assumption, we cannot show that for the fully connected neural network, we can find a good point. Because we can only if we're using the fully connected neural network, so basically we can only show that it's n to the power of d, a time algorithm. So we can make it in polynomial in n. However, it has an exponential in d kind of type of thing. However, for the for the convolutional neural network, we can show that there's basically a polynomial in both n and d time algorithm. And we can show that we can find a point theta star such that this would hold. So this means under this data assumption, and for only some cases, for only some type of the neural network, we can show that this would be true. In general, this won't be true because checking, I totally agree with Adam, because sometimes even checking whether a point is a local minimum or not would be an NP-hard problem. Okay.
Sorry,
and
can I ask a quick question about the realizability assumptions? If we just go back to the margin slides, when you say there exists a function f such that this is true in our class, like, do you mean like you fix a certain data set size and this f has n plus 1 neurons, or yeah, basically what is our class here?
Our class means there exists a single layer ReLU neural network with some bounded norm. So that is what is the neural network set. But
you're not also assuming anything about f, the number of neurons that f has?
No. So there exists a neural net. So there exists a number, and there exists a neural network with those amount of neurons, such that, and it has a bounded norm, and it can separate the underlying data distribution with some gamma. So that is what we're doing.
Okay, all right, thanks.
And any other questions? Okay. So the intuition for the main result is as follows. So basically, we only have like n data points, and we have m neurons where m is strictly larger than n. However, the n neurons are sufficient to feed the data. So why not just use the exactly n neurons? And actually, Professor Shrikant asked me this question before, and I don't have a very good question. I don't have a very good answer at that time, and even right now, we don't have a very good explanation for this. However, the intuition is more like in the higher dimension, it seems gives us more way to escape the saddle points or the bad local minimum. So this is the reason why we use the n plus 1 neurons instead of using the n neurons. Okay, and now I'm going to present the proof idea. Okay, the outline of the proof of the memorization is as follows. So at a local minimum theta star, the following condition must hold. So this is the only thing we have for the local minimum, because for the ReLU neuron, the first order condition doesn't hold, right? Because it is non-differentiable, and that will be a very hard. Actually, that is the hardness of the analysis. And this is the only condition we have for the local minimum, and we are going to exploit it. So basically, Adam, and you can see that this is the only thing we have, and this is the only thing we use, and we don't use the extra information. So the global minimum satisfies this condition, and it also has some, it has also, so it has the same kind of like performance. So we are going to use this condition to show that there is an inactive neuron at every local minimum for almost all lambda j in an interval. So you may ask, because I think you can remember that in our theorem, we're showing that for almost all lambda j's in that interval. So you may ask, okay, why almost all lambda j's, not all lambda j's in that interval? And second question you may ask is, how does the over-parameterization help? Okay, and later on we will show where this two comes from. And if we can, and so the first step we are going to show that at every local minimum there's an inactive neuron, and then we are showing that every local minimum with an inactive neuron has small training error, and at the same time we can also control the model complexity by by choosing a very good lambda, right? And together by combining two of them, we can show that the generalization performance is good. So this is basically the outline of the proof. Okay, and here is a useful facts we're going to use. So, okay, consider the mapping, the linear mapping, which is the U equals to the A and matrix A times the V equals to the matrix A times U, where the V is a m-dimensional vector and U is an n-dimensional vector, and M is larger than M. So then the image of the Rn is basically a zero measure set because it's a lower dimensional hyperplane in the Rm, right? So basically the zero measure sets in the Rm. And now if we are considering the V is a function of the U, where the function h is basically a Lipschitz continuous function, then the h of Rn is again a zero measure set in the Rm. So basically this is a useful facts we're going to use. So the step one, the inactive neuron. So the first step is we assume that all of the neurons are active at the local minimum. Then in this case, after lots of manipulations, and actually I've spent like a whole 1 year because there's a small trick to prove this would be true. And actually we've spent 1 year, and later we find out, oh, okay, it's so easy. But before that, it's kind of like, it's kind of a sad story. We spent 1 year on this little thing. And after lots of manipulation, and we can show that at the local minimum, this would be true. So because yi is basically the label for the data set I, and xi is given, is a feature vector for the data sample I, and the vj is some subspace only related to the index j, and the p of the vj, this is the vector, right? And the p of the vj is basically means we are trying to project this vector onto this subspace. And you can see that this is the indicator function, and this is the indicator function. So this is has a binary output, and the xi's, vj's, and yi's are given. So basically, you can see that you can view the whole thing as if you view the li's are some input vectors, and in this input vector has a dimension of n. And the lambda is basically an output vector, and this output vector is basically a vector of dimension m. So this is basically a mapping from the n-dimensional space to an m-dimensional space. So this means for each possible value for the indicator functions, the lambda j's, the vector of the lambda j's is a Lipschitz mapping of the L prime from the Rn to the Rm. So this means the lambda j's lies in the zero measure set. So this means if we assume that all of the neurons are active at the local minimum, then lambda j should lies in the zero merit set. So this means by contradiction, if we're going to choose the lambda j's outside of this zero merit set in Rn, then at least one neuron must be inactive at the local minimum. So this is how we prove one neuron is inactive at the local minimum, and it is also the reason why the lambda j's should be almost all lambda j's in some intervals instead of all lambda j's in some intervals. So this is a reason why it comes from.
Just giving his heads up, you have about 5 minutes.
Okay, sure. Okay, I think we're starting kind of late. Yeah, that's fine. Yeah,
sure. Yeah, people are free to stay.
Yeah, I mean, take a couple more minutes if you need to.
Yeah, sure.
Yep.
And okay, we're going to jump this. So basically, at the step 2, because we know there's an inactive neuron, and then we're going to perturb that inactive neuron, and use the facts that the theta star is basically a local minimum. So we are going to use the definition of the local minimum. And after some manipulations, we can show that the summation of the L prime is basically upper bounded by something. And if the lambda 1 is very small, then this can be viewed as the summation of the L prime is very small. And because since the L, it has the shape of this, basically this means the L prime is an increasing function. So this means if the summation of the L prime is very small, then for each part inside of the L prime, it would be negative. So this means the yi have the same sign of the L. And this is how we prove that the training error is kind of small. And the generalization part is kind of like the standard. And to control the test error, we should choose some regularization parameter lambda to trade off between the training error and the size of the model parameters. And we can also bound the Rademacher complexity of the function of the neural network. And we can show that with probability at least 1 minus delta, this would be true. So the proof for the generalization part is kind of standard. Okay. Now the key message so far is as follows. Because since each local minimum has a key property, there exists an inactive neuron. So actually, in fact, using the same proof, we can show that any point which satisfies the following 3 conditions has the same good generalization performance of a local minimum. The first one is the gradients of the empirical loss function, the regularized empirical function with respect to the coefficient A is 0. And second, the absolute value of the AI is basically equals to the norm of the WI. So which means the neural network is somehow balanced. And third, there exists an inactive neuron, and any perturbation of this inactive neuron's parameter AW increases the Ln. So if you can find some point which satisfying all these 3 conditions, then the generalization performance is guaranteed. And now the question is, how do we design an algorithm which can find the point satisfying the above things? And this is the algorithm, but since we don't have much time, basically, so the idea is basically to find the point which satisfying all these 3 conditions. And now I'm going to conclude the work. The practice that suggests that the over-parameterized neural network perform very well in both of the training and generalization. And here we prove that the over-parameterization with the regularization implies that all local minima have very good generalization performance. And there exists a polynomial time algorithm to find a good local minimum. Here, what we mean the local is some points which share some similar property with the local minimum. And the amount of the over-parameterization needed for our results is just n+1 instead of the n³ things. And actually, this matches a conjecture on numbers of neurons required for a neural network to satisfy property we never considered. So it's like the robustness. And in that paper, I think later this year, earlier this year, I think they showed that their conjecture is true. And so the idea is more like to make the neural network robust, then the numbers of neurons we need is basically n+1. And here are some open problems for our results. Can the standard gradient descent work? And we don't know. And can we show that for the stochastic gradient descent, is the generalization bound also true? We don't know. And how about for the deep neural networks? We haven't considered yet. And in this work, we only consider the regression problems we only consider the binary classification problem. We don't consider the regression problem, and we don't consider the multi-class and multiple label classification problems. And that's it. Thank you. Okay, it's 11:01.
Perfect timing. Thanks, you. Adam, are you gonna take it outside now or take some questions for a few minutes?
Yeah, let's. Well, yeah. I mean, well, definitely we should take questions.
Yeah.
Any questions?
Maybe could you say a word about the application to CNNs?
Oh, actually, I think we provide, yeah. So you wanna hear something about the results on the CNNs, right?
Yeah, I mean, briefly, yeah.
Yeah, okay. So here is the, sorry. I think we have the, okay. So for the convolution, if we're using the convolutional neural network, and if we're assuming that the function is kind of like almost the CNN separable, so this means for this underlying distribution, there exists a CNN such that it can classify with a margin at least gamma with high probability, and in some part of our algorithm, it only takes into the power of R computations to find the descent direction. And here the R denotes the size of the template. And so this is the reason how we show that for the CNN there exists a polynomial kind of algorithm. If we're using the fully connected neural network, then it will be the n to the power of d.
What's n again? N is the number of points.
N is the numbers of samples.
Okay, gotcha. Okay, thanks.
So because the CNN has the limited channel, right? Because it only takes a part of the input, and so this is the reason how we get rid of the dimension d.
I see.
So we have the dimension of that template. That would be n to the power of r.
Gotcha.
Yeah. If you're using the whole input as your input for this for each channel, then the r becomes d.
Is there any hope of getting that to like 2 to the r instead of n to the r?
I think it is possible to get the n to the power of some r to the 2 r over 2. I don't know, but we haven't tried that.
Thanks.
Yeah.
Okay, well, if there are no other questions, I mean, thanks a lot, Shiyu. That was a very interesting talk, and hopefully we'll see you again in Berkeley in a month.
Yeah, sure.
Okay, thanks everybody.